Okay, this video looks at identifying the types of chemical bonds and the types of compounds, and then how we go about naming the compounds based on their types. What we've got here in front at the top of the page is a host of different types of chemicals. And what we want to do is be able to isolate them, whether they're ionic compounds or molecular compounds. And before we do that, probably good to start off with a quick definition, some real simple definition to look at. So typically, when we talk about ionic compounds, an ionic compound is one that where we have a metal bonded to a nonmetal. And that's usually the standard definition, especially grade 9 and 10. What we're going to notice in grade 11 and then later on grade 12 is that it's not always as simple as that. And then we would typically say molecular compounds are when we have two non-metals bonded to each other, two or more. However, we need to refine our approach to identifying types of chemical bonds and the compounds that they're in. And this is where we look at electronegativity. And electronegativity, a real simple way of looking at it, is the force of attraction between that shared pair of electrons feel towards one element or another. And depending on what the atom is, it will have a greater electronegativity. Your elements that have the strongest electronegativity are found on the right-hand side of the periodic table, your halogens and oxygen. And your elements with the weakest electronegativity, of course, are your metals, especially your alkali earth and your alkaline earth metals. And so what we can actually create is a bit of a spectrum. We can look at the difference between electronegativity. So I like to look at the difference between the electronegativity to determine what the bond type is going to be. Think of electronegativity as being a tug-of-war between for the paired electrons between the two atoms, and we can take a look at how the spectrum goes from one extreme to the other, where we're increasing in the strength of one side over another. So if we want to take a look at a really even sharing, if our electronegativity difference is 0, so this is our En difference. So say I'm looking at an electronegativity difference is 0, that might be a diatomic molecule like nitrogen gas or oxygen gas. We would call this a pure covalent bond. And it turns out that we can generally say that a pure covalent bond is any bond where we have a difference in electronegativity between 0 and I like to say around 0.4. Anything between that, and 0.4 is an example of that would be your carbon-hydrogen bonds. Carbon has an electronegativity of 2.5, hydrogen has an electronegativity of 2.1, and they have a difference of 0.4. That means that carbon and hydrogen are pretty much equal in that battle for the pair of electrons between the two of them. We do hit a sort of a magic number. It's almost in between, and that number is 1.7. Anything beyond 1.7, and we are now into the ionic area of the spectrum. So any two elements that have an electronegativity difference of 1.7 or more, and it turns out that that's when you have metals and nonmetals, you now have an ionic bond. However, the interesting thing is sort of as we go from 0.4 and we get closer to 1.7, what we notice is that the sharing is imbalanced. And what we find, what I like to say is anything around 0.8, between 0.8 and 0.7, the tug of war is very one-sided. So it's, we could say, an unsymmetrical sharing. Anything from 0 to 1.6 would be covalent bonds. Anything 1.7 or greater would be ionic. But as we go from 0.8 to 1.7, especially the closer we get to 1.7, we get the sharings non-symmetrical, which means the shared pairs spend more time closer to one atom than the other, which creates a dipole where you have one end of the bond takes on a slightly negative charge because the electrons spend more time by it, and the other end takes on a slightly positive charge. And because that, we would call this polar covalent. And so that's a polar covalent bond. And so this starts to help us understand what we're dealing with. And then it makes it a lot easier for someone to start to move a lot of these compounds into their correct places. So, you know, the obvious ones are when we have metals and nonmetals. Right here we have what would be a binary compound, the FeF3, but here we have an oxoanion. We're going to talk about those in a second. We still have a metal bonded to a group of nonmetals that seem to be acting as one unit. We can call those polyatomic ions. And here we've got some examples of some molecular compounds. And we could go through this and separate all these. Where it gets interesting is sometimes we have examples of compounds like ammonium hydroxide, which technically you only get in solution. But ammonium hydroxide is made up of two sets of molecular compounds, but ammonium and hydroxide, when dissolved in water, are ions. So it acts like an ionic compound when it's in solution, but it's also a molecular compound. And so this is where we start to notice that the world of chemistry isn't always as cut and dry and as simple. But definitely take a second, maybe pause it here, and see if you can separate all of the different compounds into the correct group. So it might be a good time to pause it here. One thing to remember, even though acids do form ions in solution, they are molecular compounds. So something like this, H2SO4 or HCl, these are both acids. This is sulfuric acid and this is hydrochloric. They are molecular compounds. So we do have to denote them as that. However, you can force them to break apart, dissociate into ions if they're in the right type of solution. So go ahead, pause, and separate these, and we'll move on to the next slide. So we're looking at molecular compounds and the way that we can name them, identify them, and name them. I want to draw your attention to the look fors. These are the things that whenever we go to name or we go to write out the chemical formulas, we need to make sure that we look for. All names need to start with lowercase letters. Um, we're going to notice that we use prefixes for naming, and I'll show you an example as to why really quick here. Carbon will bond with oxygen to make two different types of molecules. One carbon will bond with two oxygens, and this is what we call carbon dioxide. And carbon will bond with one oxygen, and this is carbon monoxide. Now, each of these has different chemical properties. Carbon dioxide, we breathe it out. You're breathing it out right now. In fact, you're breathing a tiny bit back into your body, and it's not doing any damage. Carbon monoxide, on the other hand, goes into your bloodstream, attaches itself to your hemoglobin, and your red blood cells can't get rid of it. If you were to breathe in enough of this stuff, it would kill you. It's a poison, a toxin, because it will disrupt bodily functions. Carbon dioxide, not the same thing. And so when we talk about or when we name molecular compounds, we need to use prefixes like di and mono to describe how many atoms of the elements that we see. We typically do not use mono for the first element. In this case, we wouldn't call this monocarbon monoxide, but we will use it for the second one if it's possible to have different different situations, like carbon can be bonding with two oxygens or one, carbon dioxide versus carbon monoxide. Another example would be something like N2O5. This would be called dinitrogen pentoxide. All right. So we need to explain that we have two nitrogens and five oxygens, because nitrogen can make many different combinations with oxygen. Especially when you start to learn some atmospheric chemistry, it's interesting to see all the different things that nitrogen can possibly make in terms of molecules. And so each of these would have its own name: nitrogen monoxide, nitrogen dioxide, nitrogen trioxide, dinitrogen pentoxide. And so it's important that we use the prefixes. And the most common ones are mono for one, di for two, tri for three, tetra for four. So if we have something like this, this would be, this could be called carbon tetrahydride. However, because it is an organic compound, it has another name used, and we call it methane. But the tetra corresponds with the four hydrogens attached to the carbon. Now, molecular compounds can also form polyatomic ions, and you might have seen these before. We noticed that in one of the compounds, you'll notice an NO3 group that has brackets around it. And you might ask yourself, well, what is that? What it turns out is that NO3 can bond together, nitrogen and three oxygens, and it can hold an extra electron. And because of that, this unit actually acts like an ion. So it's got a charge on it, it's got an extra electron, and because of that, it can give that electron to something else and then make a chemical bond, or it has stolen an electron from a metal, and now will form an ionic compound. Polyatomic ions are molecules that hold a charge, thus they're ions. This one is called nitrate. And there's a whole host of them. We're going to take a look at them now. But it is possible for a group of atoms to be bonded and then also hold a charge. So not only are they molecules, but they're also an ion as well. And depending on what they combine with, they will either be part of a molecular compound or they could be part of a ionic compound. If we take a look at some common polyatomic ions, or a lot of times they're called oxo ions or oxo anions. We call them that because they've got a whack of oxygens on it. We can see there's 3 on nitrate, 3 on chlorate, 3 on fluorate, and we can see all of these here. A good way of remembering how we get these is to think of them as being part of an acid. If I put nitrogen onto a nitrate, I have nitric acid. Now, how does nitrate take a +1 charge? Well, how many hydrogens is it going to lose? It's going to lose 1. And so if I have 1 hydrogen that comes off the nitrate, then the nitrate takes a -1 charge. -1 plus 1 adds up to be 0. So you add those two together and you get nitric acid. Just a way that you can remember it. Look at your sulfate there. Most people remember that sulfuric acid. That's H2SO4. So where does sulfate get its 2 minus charge? Well, it gets it from the fact that it's going to lose 2 hydrogen. So if sulfuric acid loses 2 hydrogen, you get a sulfate ion. And that's maybe a simple way of trying to remember things like that. We have some other electronegative radicals. We have hydroxide, very important, bicarbonate, which is, you could think of carbonic acid, H2CO3, only losing 1 proton. And if that happens, again, a proton is an H plus ion, you get a bicarbonate ion. And bicarbonate ions have interesting properties when it comes to acids and bases. We have cyanide. The one interesting thing is there's only one real electropositive radical that we ever deal with, and that's ammonium, NH4. And it has a +1 charge. So these are all your polyatomic ions. Again, they are molecular compounds that have either accepted or lost an electron or many electrons and taken a charge. Now, one of the important things to remember when we're dealing with these is that there's some naming that we have to be aware of. So I'm just going to get rid of this stuff right here for a sec. Now, it's possible for something like nitrate, which is NO3, this is called nitrate, it's possible for nitrate to lose an oxygen. And if nitrate, due to some chemical reaction, loses an oxygen and becomes NO2, it's still going to have the same charge, but we call it nitrite. Alright? Notice that with an oxoanion, the normal state for it is ATE. However, if I lose 1 electron, I put an ITE at the ending. If I lose 2 oxygens, then it would be hyponitrite. And here I would use a prefix hypo and ITE for the ending. Now it's also possible to gain an extra oxygen. Again, charges do not change. but we call this hypernitrate. And so what you will have to try and do is memorize the normal state of oxygens. A good chunk of them have 3 oxygens. But then we have our sulfate, our phosphate, that have 4. And so, if you can just remember that all of them normally have 3, except for sulfate and phosphate have 4, maybe that will help you out as you go through this. You don't have to worry about hydroxide gaining or losing oxygen. Bicarbonate you can have bicarbonate, and that can definitely happen, but cyanide, you don't have to worry about that. So now that we've talked about these ions, we can go back and look at the various different types of ionic compounds. And so when we look for ionic compounds, we've got a whack of look-fors that we need to take into consideration here. Ionic compounds can always be recognized by the presence of a metal or of ammonium, which is NH4. So if ammonium's there, you've got an ionic compound. They don't form molecules, they form crystals, and that's really important to understand. We'll talk about that a little bit later when we look at structure of molecules and how they differ from ionic compounds. And what we do is we name the compounds by stating the name of the ions that are present. Again, always in lowercase. We're going to start with really simple ones here, like a binary monovalent compound. So let's go through that. What does that mean? Well, say I've got NaCl. Well, Na is sodium. Whenever we name the metal, we don't change any part of the name. However, when we name the nonmetal, we do put an ending on it. We put an IDE ending on a simple ion like that. We have a binary compound, meaning that there's only 2 elements. Only 2 elements present. In this case, sodium chloride. And we say it's monovalent because your metal has only 1 charge possible. And hence that makes it a binary monovalent compound. So something like zinc. If we have this, it's simply zinc chloride. Now we don't say it's zinc dichloride. We don't worry about the number of elements, because in this case zinc can only make bond in the ratio of 1 to 2. Why might that be, you ask? Well, say I went backwards. Say I wanted to figure out, well, if I was given zinc chloride, what would be the chemical formula? So what I would do is I would write down my ions that would be present. So I'd have a zinc plus ion, a 2 plus ion, and a chlorine 1 minus. And I write my charges above. And I say, okay, well, what's my compound going to look like? Well, what I can do here is I can cross my charges over. And when I cross my charges, I don't worry about the signs anymore. So my zinc would take a 1 charge, so we don't bother writing it in. But the chlorine would take the 2. And so, when that 2 comes down, that tells me that I need 2 chlorines to satisfy zinc. Now, does that make sense? Well, let's see. Zinc's got a 2 plus charge, and I need 1 of them. So that gives me a plus 2 from the metal side. And chlorine has got a minus 1 charge, and I've got 2 of those. So that's a minus 2. Plus 2 minus 2 gives me 0. And your charges need to add up to 0. That's grade 9 10 stuff. So now let's take a look at something that could be that's binary but multivalent. What does that mean? Well, binary again means we've only got two different elements. So let's look at something like this. Now, copper is interesting because copper can bond 1-to-1 with chlorine, but it can also bond in a 1-to-2 ratio. Two different ionic compounds, both with different chemical and physical properties. So how do we name them? Well, we need to name them based on the charges. What would the charge on copper be here? Well, we always know that chlorine's got a charge, sorry, not +1, of -1. If I have one copper, then that means it must have a charge of +1. Hence the name here is copper 1 chloride. And I use a Roman numeral. We call this the stock rule. And I use a Roman numeral to denote the charge on the copper, because if I know the charge on my metal, then I can figure out very easily how many atoms of my nonmetal I'm going to need. Now notice here that chlorine, again, -1 charge, but I've got two of them. So that must mean that copper has got a +2 charge. So this would be copper 2 chloride. Now there's an old way of naming, what we would call the classic name way of naming. You may have seen copper 2 chloride called cupric chloride, or copper 1 called cuprous chloride. We'll take a look at that in a bit when we look at a classical way of naming our ions. But the stock rule is the method that we use for naming. Today it is the accepted way. And in some cases, our metals can have more than one charge. So when we talk about multivalent, that means metals that can have two or more charges. Like manganese can have 4 different charges, which is kind of interesting. So we have to know exactly what form of that metal we're dealing with. Now, we're not quite over. It's also possible to have polyatomic ions. So we could have sodium connected with a nitrate. And so this would be just simply sodium nitrate. We could also have sodium with NO2. Now notice the difference between the 3 and the 2. The charge on this unit stays the same as -1, but it's not nitrate, it's nitrite. So this would be sodium nitrite. Alright, and we could get this even more interesting. We could have CuNO3, which is copper 1 nitrate. We could have CuNO2. So what's happened here? Well, I don't have nitrate, I've got hyponitrite. And the charge on hyponitrite is always -1. I've got 2 of them, so that must mean the charge on my copper is +2. So obviously I'm dealing with copper 2 hyponitrite. And that's as complex as these things can get when we're dealing with ionic compounds. Now what I've got here for you is some practice that you can do. I've given the name of the compound. You let me know if it's ionic or molecular, and you give me the formula, or vice versa. I've given you the formula and you tell me what the name of it. And I've got 2 rounds of this. So I've got one group right here and one group right here. Write these out, pause the video, write these out, and then I'm going to flash up the answers. Okay? Okay, so here are the answers to the questions. Make sure you check through and see that you've done them correctly. And what we're going to do now is just quickly move on to the classical way of naming, just so that you've got some exposure to that. So back in the good old days, ions, before it was understood that some ions could actually have more than 2 different charges, there was a method of naming where we use the endings "ic" and "us. And this is typically used with acids now, with the oxo acids, but we'll get into that a little bit later. But what we have here is an example of iron. Iron is a multivalent um, um, metal, and it can have a charge of +2 or +3. Now, what we do here with the classical method is we use the ending "ic" when we have the greater charge, and the ending "us" when we have the smaller charge. So if I had something like this, this under the classical old school name would be called ferric chloride. The reason why for that is we know that chlorine's got a charge of -1. If I've got 3 chlorines, then that must mean my iron must have a charge of +3. The stock system name, of course, would be iron 3 chloride. Simple. Now, if we have FeCl2, all right, that would be ferrous chloride, or iron 2 chloride. Alright, so you will have to know of this. You won't see a lot of it in our class, but you will have to know this system, because it is used in some books and on some labels of compounds that are shipped out, and so you might see this in a lab. The last thing I do want to go over is acids and bases, just very simple acids and bases nomenclature. And so we're just going to break this down. We definitely are going to go a lot further into acids and bases with another unit, but I do want to take a look at some very simple naming. So acids are typically when we have a hydrogen attached to a nonmetal. We'll just call that X. So anytime we have hydrogen attached to a nonmetal, we have an acid, and it's when it's out in front. And so an example is a binary acid, which would mean hydrogen with 1 nonmetal. An example of a pretty common one, in fact it's in your stomach right now, is hydrochloric acid. Notice that when we name binary acids, we use the prefix hydro in front of the nonmetal's name. So hydrochloric acid, HBr would be hydrobromic acid. All right. So again, we use the prefix hydro. Whereas an oxo acid like this would be just called chloric acid. So again, an oxo acid means we've got a whack of oxygens. Now it's possible to have something like this. I've lost a oxygen. And so this is where we use sort of like the classical ion system of naming here. We would call this chlorus acid. And if it was HClO, it would be hypochlorous acid. If it was HClO4, it would be hyperchloric acid. And so we use a combination of those systems there to name it. Bases, on the other hand, for now, we're just going to keep these really simple. Bases are when we have a metal or ammonia bonded with hydroxide. An example of one, it's called in industry, it's called caustic soda, would be NaOH. And that's just simply put sodium hydroxide. Another example of one would be CaOH2, and that would be calcium hydroxide. And say I asked you, well, what does aluminum hydroxide look like? Sort of work backwards. I've given you the name, determine the chemical formula. Well, again, we write the charges of the ions. So aluminum has a +3 charge, and hydroxide has a -1 charge. And so we would go back and we would cross our charges down. And what's really important to remember is this unit, OH, needs its one complete unit. So we put brackets around it because we need more than one unit. So it would be AlOH3. And that's what aluminum hydroxide looks like. And that's a really quick breakdown of types of compounds that we're going to see in the course, and some basic nomenclature on all of them. And checking out our website, I'll have a lot of worksheets, so make sure you take the time to go through that.